So next, we're going to look at another example of finding the equation of a tangent line to a function at a point, using our definition of derivative that we just found. So in this case, I want to let my function be f of x equals 1 over x plus 3, and we're going to try to find the equation of the tangent line at a equals -2. So before we get started doing any computation, let's take a look at the graph of this function. So I've already typed into my calculator. Oh, that's pretty blurry. Let's see if I can focus it on my calculator. Ah! Ugh. So next, we're going to find the equation of the tangent line of a function using our definition of derivative that we just talked about. So we're going to do just another additional example, and this time my function f of x is going to be equal to 1 over x plus 3, and we're going to find the equation of the tangent line at a equals -2. So before we get started plugging in and looking at our definitions, let's look at a graph of this. So I've typed into my calculator the function, and let's see if I can focus in on this a little better. I guess that's better. So this is 1 over x plus 3. When I graph this, see that I get a function that's asymptotic, and it looks like it has a rip. If I plug in -3, it gives me this value. So I'm going to sketch that graph here. We see if x is exactly equal to -3, we get 1 over 0, and our function looks something like this. And so we can estimate, looking at this graph, what the tangent line at x equals -2 might look like. I know that it's going to have a negative slope. I'll draw this one in red. It's going to have a negative slope, and from my picture, I'm not sure whether the y-intercept is going to be positive or negative. This isn't quite accurate enough to be able to tell that. But this is the idea. This is what we're trying to go for. Before we go too much further, I also want to notice, what is this point? We're plugging it in when x, or a in this case by this notation, is equal to -2. And so the height here is going to be at f of -2. And looking at this graph, we can quickly, or looking at the equation, we can quickly plug in what is f of -2. It's going to be 1 divided by -2 plus 3, which is equal to 1 divided by 1, which is 1. So I know that this is at the point -2, 1. I just don't know what the slope of the tangent line is in this case. So let's use our definition of derivative to be able to compute the tangent line. So my step 1, other than drawing a picture, I suppose, we don't have to draw a picture every time, I want to find the slope of the tangent line at a equals -2. And to do that, we're going to use our definition of derivative. So in this case, I'm going to look at the limit as h approaches 0 of f of a plus h minus f of a all over h. And recall, that's saying that as my h values get closer and closer and closer to 0, the difference in my y values over the difference in that h is getting closer and closer to 0. And so that's honing in on what the slope will be right at that point. Let's plug in some of the information that we know about this function. So first, I'm going to drop the limit notation because I'm going to write out a lot of algebra, and I don't want to have to rewrite that, but that's going to be implicit here. We're going to look at what is f of a plus h. Recall that in this case, a is equal to -2. So I can plug that in, and I say that this is f of -2 plus h minus f of -2 all over h. Now let's go ahead and plug these values into our function. Our function in this case is 1 divided by x plus 3. So when I plug this into the function, this whole piece is getting plugged in where my x value is. So it's going to be 1 over x plus 3. This whole piece becomes my x value. So I get -2 plus h plus 3. This is f of -2 plus h. And now I'm going to subtract f of negative 2, I'm going to plug in negative 2 for my x value. So this becomes negative 2 plus 3, all divided by h. So this looks really clumsy as it's written. Let's simplify it a little bit before we move to the next page. So in order to, let's look at this first fraction. In the denominator I have minus 2 plus h plus 3. Notice that these parentheses here don't imply any sort of multiplication, that each of these are individual terms. So I can add the positive 3 with the minus 2, and I end up with h plus 1 in the denominator here. So I have 1 over h plus 1 in the denominator. And then this simplifies nicely. 1 divided by 3 minus 2 becomes 1 over 1, which is 1. Where did this 1 come in? Notice this is just f of negative 2. We already found what f of negative 2 was when we were analyzing our graph. F of negative 2 is 1, which matches what we're doing down here. Okay, all divided by h. This is looking a little nicer, but it's still not great. I have this fraction in the numerator, and I might want to simplify this numerator. So let's turn the page and recall that we have 1 over h plus 1 minus 1 all divided by h. So in order to simplify this numerator, I'm going to get a common denominator. This has the denominator of h plus 1, so I'm going to multiply my 1 by h plus 1 over h plus 1. This is a clever version of 1, so now I'm left with my first fraction, 1 over h plus 1, and then I subtract the second fraction, h plus 1 divided by h plus 1. I'm not doing anything with this h on the bottom. So now that I have a common denominator, I can subtract across, and I'm left with, this is equal to 1 minus the quantity h plus 1, all divided by h plus 1 over h. Let's simplify the numerator of this. It's this whole quantity of h plus 1 is being subtracted, so I can distribute this subtraction to rewrite this as 1 minus h minus 1 divided by h plus 1 all over h. And again, this numerator simplifies 1 minus 1, leaves me with just a negative h on top. Now we're getting somewhere. Negative h divided by h plus 1 all divided by h. It's still not great because I still have a fraction divided by a fraction. I want to get rid of this h on bottom. For some of you, you might want to think of this as an h over 1, and this is the division of fractions, and you have memorized the rule of inverting and multiplying. It's a rule that I hate because it doesn't intellectually make sense why I would want to invert and multiply anything. So instead, I'm going to think of this as a division of fractions, and I want to make the denominator equal to 1. So I'm going to multiply the bottom of this big fraction by 1 over h, and I'm also going to multiply the top of this big fraction by 1 over h. I'm not changing anything, I'm just multiplying by a clever version of 1. In this case, the clever version of 1 is 1 over h divided by 1 over h. But look what happens. It means that my denominator values cancel one another, and I'm left with just a 1 in the denominator. I also notice that my negative h and h cancel, leaving me with just a negative 1 on top. What does that mean? So now I have a negative 1 in the numerator of the numerator, divided by h plus 1, and this denominator, those h's canceled, and I was left with just 1, which is in fact, negative 1 divided by h plus 1, because a 1 in the denominator here is just like 3 divided by 1 is the same thing as 3. Negative 1 divided by h plus 1 divided by 1 is just what this numerator is. Phew! So we just did all of that work, and why did we do all of that work? Let's remind ourselves what we were up to. So we were trying to find the limit as h approaches 0 of this value, because that's going to tell us our derivative when a equals -2. So we just did a bunch of work to simplify this, and now we need to take a limit. So let's consider the limit as h approaches 0 of -1 divided by h plus 1. Notice now this is a continuous function, and when I evaluate this limit, I can actually evaluate this value by just plugging in h equals 0. So because this is continuous, we can plug 0 in and we get -1 divided by 0 plus 1, which is just -1. So this tells me that the slope of my tangent line is -1. So if we go back to our original picture, that makes sense that this red line, it actually looks really close to a slope of -1 because it's going down as it moves in the positive x direction. And in the last video, we saw a fancy equation for being able to plug in what our derivative was going to, what the equation of our tangent line is going to be. And that equation was given by y equals f prime of a times x minus a plus f of a. So this is our equation of tangent line. If you did not want to memorize this, you could instead use the skills that you know from equations of lines. We know the slope of the line. We found that the slope of this line is -1. We also know a point on this line. The point, recall, we found that when we were first analyzing the graph, our point is at -2, 1. Usually it's at a, comma, f of a, and in this case, our a is -2 and our f of a is 1. And we can use the skills that we know from previous math classes to be able to find the equation of a line given a slope and a point. Normally when we look at equations of a line, lines are given by y equals mx plus b, right? Where m is the slope and b is the y-intercept. I don't have the y-intercept though, I just have this point, right? And I'm not talking about the y-intercept of the function, because the function is going to veer off and do other things. We're talking about the equation of the red line. So I'm going to use the slope and the point to solve for this. Namely, I know that my slope is my m value is -1, so I'm going to plug that in, because that's my slope value. I know what my x point is in this case. My x point is -2. My y value at that point is 1, and I'm going to find out what b is. So when I get -1 times -2, I end up with 2. So 1 equals 2 plus b. In order to solve for b, I'll subtract 2 from each side, and I get that -1 is equal to b. What does this tell me? This tells me that the equation of my tangent line is going to be -1 times x plus -1, or -1. And this is the equation of the tangent line of my function at this red line. So this graph, you can see, isn't quite accurate enough because I think visually this 1 is too high, that it should be shrunk down a little bit so that my tangent line should intersect down at a negative value. So, and finally I could rewrite this as y equals -x minus 1. Notice the difference between the equation of the tangent line, which is always a line, and the equation of our original function. Our original function might do all sorts of crazy things. The equation of our tangent line is always going to be the equation of a line.